This video is about Newton's law of gravitation, and I suppose we should state it that the force between two bodies is given by this expression, where m is the mass of one body, the bigger, and little m is the mass of the smaller body, r is the distance between the two bodies, and big G is a constant. Now big G is actually quite small. It's 6.67 by 10 to the minus 11 Newton square meters per kilogram squared. Now imagine two bodies of the same mass, say 1 kilogram, separated by a distance r of 1 meter. How strong is this gravitational attraction? Well, substituting those numbers into our formula, we just get F is big G, and that's quite small, 6.67 by 10 to the minus 11. And this, of course, now is measured in newtons. So it's quite a small force, and it's probably a good thing that it is, because we wouldn't want two people 1 meter apart attracted to each other by a profoundly strong force. They'd never separate. I could think of nothing more by way of a miserable outcome for humanity to be so closely bonded under such a powerful force. Well, we need some preliminaries. Now, the first one is the solution to this second order differential equation, d2y by dx squared plus y equals some arbitrary constant c. Well, not just arbitrary, but a constant c. What is the solution to this? Well, without much ado, we'll just state it. It's a cos x plus b sine x plus c. It's easy enough to verify. If we take the first derivative, we just get minus a sine x plus b cos x, and then the second derivative, y double dash, is minus a cos x minus b sine x. And it's pretty easy to see that y double dash plus y, just the sum of these components, they disappear, some of those two components disappear, and we're left with C. So this really confirms or verifies that this is the solution. In fact, it's the general solution, and it may be written in a more compact format, y equal to, say, r cos x plus beta, say, plus the C. So there's the general solution. Now the second thing we need, by way of preliminaries, is the equation of a conic in terms of polar coordinates. So supposing we have a section of a conic, perhaps an ellipse, and there's its focus, F, and some point up here, P, with coordinates x, y. We'll draw in a directrix at x equals d, and a line from F to P, and another one from P to meet the directrix at a right angle at M. This length here from F to P is r, theta is the angle just in there. So we have, by definition of a conic section, that FP over PM equals E. E is the eccentricity of the conic. So what is FP? FP is just EPM, FP is R, PM is D minus X, and the X is just r cos theta. Now it just requires a little bit of rearranging there. R would be ed over 1 plus e cos theta. And so there is the equation of the conic. Oops. Now, from there, let's have a look at Newton's law once again. It says that F is big G, big M, little m on R squared. Let's write that in terms of complex numbers, or using complex numbers. We can write the R as mod Z of T squared. Now, what's Z? Z is the complex number sitting here at P. And so, because P is a point which is in motion, the position of Z will depend on time. Now we can go one step further and express this as a vector. We'll write F in vector notation. We've got big G, big M over little m, mod ZT squared, and we'll write this as minus Z of T over mod Z of T. So this corresponds to the unit vector r hat. R hat, of course, would be this vector from F to P, the position vector of the point P, relative to the origin F. So here we have a more compact vector representation using complex numbers. We'll call all this term up here K, little m, Z of T over mod Z of T cubed, where K is big G times big M. Now F we're going to look at. This is the force acting on the mass at the point P as it moves. So there's F, the focus, and we're going to assume that the mass big M is sitting there and that the mass little m is at the point P, and it's going to be under the influence of big M. So with that in mind, we can go back to here and write F as little m Z double dash T equals minus K little m Z of T over mod Z of T cubed, and therefore Z double dash is just equal to minus K Z of T over mod Z of T cubed. Now the next step in this is to, oh gosh, rub this out. The next step is to write Z in its polar form. So it's going to be Re to the I theta, where both the R and the theta are going to be functions of time. I think it's fairly obvious why that must be so. So that means that Z double dash of T on the right hand side can be just reduced now to K R e to the I theta, and on the bottom mod Z is just R cubed. So that reduces to to K over R squared e to the I theta. Good. Well, having got that much, let's now go back to work out the derivatives, first and second order derivatives of Z of T. bearing in mind that both the r and the theta are functions of time. So what's dz by dt? This is just going to be dr by dt times e to the I theta plus r I d theta dt times e to the I theta. Now we can take out the e to the I theta, so we get dr by dt plus ir d theta dt e to the I theta. And now we need to differentiate that. So the second derivative, so we've got to differentiate this, keeping that fixed, and then the other way around, keeping that fixed and differentiating this. It's just using the product rule. So off we go, d2r by dt squared plus I r d2 theta by dt squared plus I dr by dt times d theta dt times e to the I theta plus, and now we leave this term alone and differentiate this one. And the derivative of this thing is I d theta dt times e to the I theta. Now the next step requires a factorisation of this. So we're just going to, if you got another page up, so off we go. Now what we're doing is factorising this entire expression just here. So let's do that. So we're going to write that as d2 z by dt squared equal to, well, we'll collect together all the terms that are real. So there's one up there, which is this one, d2r by dt squared, and the other one is over here, r times d theta dt squared. So we'll take those two first up. So we've got d2r by dt squared minus r d theta dt squared, and then there's the imaginary part. Now the imaginary part is, so there's one term there, there's another one here, and this one times that is the other imaginary one. Now two of these are product terms, that one and this one here, so that's a duplicate of the same thing, and then there's this one. So feeding those together gives us r d2 theta by dt squared plus 2 dr dt times d theta dt, and then the whole thing